Continuity at a point. Hello everyone, let's begin our session on continuity at a point. To start, let's look back at what we've already covered. In our previous section, we approached the concept of continuity intuitively. You likely remember that we described a continuous function as a graph that can be drawn smoothly on paper without ever lifting your pen. While that visual approach is helpful for getting a general feel for the concept, it isn't sufficient for the level of precision required in mathematics, especially for grade 12. To move forward, we need a rigorous, formal definition. This will allow us to move beyond just looking at a graph and instead use mathematical proof to determine whether a function is truly continuous at a specific point. In the upcoming slides, we will define exactly what this rigor looks like and establish a clear, three-step checklist you can use to solve these problems accurately. The formal definition of continuity. Now that we have established the intuitive idea of continuity, the notion of drawing a graph without lifting your pen, we need to transition to a more rigorous, mathematical definition. This is essential for the level of precision required in grade 12 mathematics. First, let's look at the formal definition. A real-valued function, which we will call f, is said to be continuous at a specific point, c, in its domain, if the limit of the function as x approaches c is exactly equal to the value of the function at c. To express this mathematically, we use the equation. The limit of f of x as x approaches c equals f of c. What this simple equation actually implies is that as we move closer and closer to the point c from either the left or the right side, the value that the function is approaching must be the exact same as the actual value assigned to the function at that specific point. In the next slide, we will break this definition down into a three-step checklist to make it easier for you to verify continuity in your problems. The three-step criteria for continuity. Now that we have established the formal definition of continuity, let's look at how we actually apply it in practice. To prove that a function is continuous at a specific point, x equals c, you must verify that the following three conditions are satisfied. It is important to remember that this is a strict checklist. If any one of these three conditions fails, the function is immediately classified as discontinuous at that point. Step 1. The function must be defined at c. This means that when you plug the value c into the function, the resulting value, f of c, must actually exist. For example, if substituting c into the function results in a division by 0, the function is undefined at that point, and therefore it cannot be continuous. Step 2. The limit of the function must exist as x approaches c. In other words, the limit of f of x as x approaches c must be a single, finite value. To verify this, we must ensure that the left-hand limit and the right-hand limit are identical. Specifically, the limit of f of x as x approaches c from the left must equal the limit of f of x as x approaches c from the right. Step 3. The limit must equal the function value. This is the final piece of the puzzle. The value we obtained from the limit in Step 2 must be exactly the same as the function value we found in Step 1. Mathematically, we are checking that the limit of f of x as x approaches c is equal to f of c. By following these three steps, you can rigorously determine the continuity of any function. To help you visualize these technical requirements, I will explain a real-world analogy involving a bridge in the next slide. Real-world analogy, the bridge. Now, to help you visualize the three rigorous mathematical conditions we just discussed, let's use a real-world analogy. Imagine you are driving a car across a bridge. First, let's look at condition 1, which is whether the function is defined. In our analogy, this means there must actually be a piece of road at the specific point. See, if there is a hole in the bridge at that exact spot, you cannot stand there, and therefore, the path is not continuous. Next, we move to condition 2, which is the requirement that the limit must exist. For this to be true, the road coming from the left and the road coming from the right must meet at the exact same height. If the left side of the bridge is 10 meters high and the right side is 20 meters high, there is a jump in the road. In this scenario, the road is not continuous because the two sides do not align. Finally, we have condition 3, where the limit must equal the function value. This means that the point where the roads meet must be exactly where the bridge surface is located. If all three of these conditions are met, you can drive across point C smoothly and without any interruption. This is the essence of continuity. Now that we have a conceptual understanding, let's apply these steps to some worked examples in the next slide. Worked examples. Now that we have established the formal definition and the bridge analogy, let's put our 3-step checklist into practice with some worked examples. Let's begin with example 1, where we are verifying the continuity of a simple function. We want to determine if the function f of x equals 3x plus 2 is continuous at the point where x equals 1. Following our first step, we check if the function is defined at x equals 1. By substituting 1 into the equation, we get 3 times 1 plus 2, which equals 5. Since we have a real number, the function is indeed defined at this point. Next, we move to step 2, checking if the limit exists as x approaches 1. For the expression 3x plus 2, as x gets closer to 1, the value approaches 3 times 1 plus 2, which is 5. Because this is a simple polynomial function, the left-hand limit and the right-hand limit are identical. Therefore, the limit exists and is equal to 5. Finally, for step 3, we compare the limit and the function value. We found that the limit as x approaches 1 is 5, and the function value at 1 is also 5. Since these two values are exactly the same, we can confidently conclude that the function is continuous at x equals 1. Now, let's look at example 2, which is slightly more complex because it involves a piecewise function. These are the types of problems where you must be extra careful, as we will see in our next slide on common mistakes. In this case, the function is defined in two parts. It is x squared if x is less than or equal to 2, and it is 3x minus 2 if x is greater than 2. We need to determine if the function is continuous at the boundary point, x equals 2. Starting with step 1, we check if the function is defined at x equals 2. Looking at our conditions, x equals 2 falls into the first piece, x squared. So 2 squared gives us 4. The function is defined. Step 2 is critical for piecewise functions. We must ensure the limit exists by checking both sides. First, for the left-hand limit, as x approaches 2 from the left, we use the first piece, x squared, which results in 4. Second, for the right-hand limit, as x approaches 2 from the right, we use the second piece, 3x minus 2. Calculating 3 times 2 minus 2 also gives us 4. Since the left-hand limit and the right-hand limit are both 4, the overall limit exists and is equal to 4. For the final step, we compare the limit and the function value. The limit as x approaches 2 is 4, and the function value at 2 is also 4. Because they match perfectly, the function is continuous at x equals 2. Common mistakes to avoid. Now that we have walked through the worked examples, it is crucial to discuss some common pitfalls students often encounter when determining continuity. First, avoid the mistake of assuming that a limit exists simply because the function is defined at point C, as we discussed in our 3-step criteria. Having a value for f of c is only the first step. A function can have a specific value at that point, but if the left-hand limit does not equal the right-hand limit, you have what we call a jump in the graph, which results in a discontinuity. Secondly, when dealing with piecewise functions, like the one we just solved in example 2, be careful not to ignore the left-hand and right-hand limits. It is a common error to simply plug the value into one of the equations and assume that is sufficient. To be rigorous, you must check the behavior from both sides of the boundary point to ensure they meet perfectly. Finally, let's clarify a conceptual point. Do not confuse the limit with the function value. It is important to remember that the limit of f of x as x approaches c describes how the function behaves as it gets closer and closer to c, but not necessarily at c itself. On the other hand, f of c describes the exact value assigned at that specific point. Continuity is essentially the bridge that connects these two concepts, ensuring that the approach and the destination are the same. Keeping these distinctions in mind will help you avoid errors as we move toward our final summary and key takeaways. Key takeaways. All right, let's wrap up everything we have covered in this lesson. To summarize, continuity at a point simply means that if you were to look at the graph at that specific x value, there are no holes, no jumps, and no breaks. It is exactly like the smooth bridge analogy we discussed earlier. This leads us to what we can call the golden rule of continuity. In formal mathematical terms, the limit of the function of x as x approaches c must be exactly equal to the function of c. This single equation is the heart of the entire concept. To ensure you apply this correctly in your problems and avoid the common mistakes we just mentioned, always follow this three-step checklist. First, verify that the function of c exists. In other words, the function must be defined at that point. Second, confirm that the limit of the function of x as x approaches c exists, which requires the left-hand limit to be equal to the right-hand limit. And finally, the value you get from that limit must be exactly the same as the function value. If all three of these conditions are met, you can confidently state that the function is continuous at that point.